Welcome back to Machine Learning Guide, episode 34, Large Language Models, or LLMs. Now, I have 3 episodes, starting at episode 18, on foundational material for natural language processing in general. This includes things like bag of words, TF-IDF, tokenization. I have 2 episodes on deep natural language processing that introduces the concept of recurrent neural networks, embeddings. We'll talk about embeddings a little bit in this episode. And then the last MLG episode 33 was transformers. And really, LLMs, if you want to understand the true core heart of LLMs, you got to understand transformers. So that episode, Transformers, is the real heart and engine of LLMs. So listen to that episode if you want to understand LLMs properly. This episode's going to add a little bit of what we may have missed that goes into modern day large language models. What are some of the new interesting techniques that they're experimenting with and going into the future? So this is sort of to just fill in the knowledge gaps on things that we haven't covered and wrapping up the LLMs package. 2017 white paper, Attention is All You Need, introduced the transformer architecture. Transformers being a sequence of attention layers, especially self-attention layers, followed by feed-forward layers and various other components in that stack. Again, listen to the last episode on transformers if you want to understand it. And the reason for the transformers architecture is that unlike RNNs, which have to predict next tokens and be trained sequentially due to the nature of the architecture, the transformers architecture takes that attention mechanism, which was introduced in RNNs, and applies it to a more traditional deep learning architecture that can train these sequences in parallel and run them in parallel. It improved the throughput of training and running these models at scale. And then once they started doing that, they started iterating on this architecture rapidly with significant changes over time. So in this episode, I'm going to talk about scaling laws, which are some interesting findings in research that dictate the amount of scaling you want to impose on the architecture, on the data set, and on the amount of training. Emergent abilities, like a model's ability to provide answers for questions it's never been asked before through generalization, which is quite a magical concept and I think was somewhat surprising for researchers. Architectural evolutions to the transformers architecture, things that have changed over time, like the introduction of mixture of experts, or MOE, which allows for greater scale and efficiency. I will talk about training, tuning, and alignment, so supervised fine-tuning, reinforcement learning from human feedback, and I'll talk about reasoning and interaction, such as chain of thought prompting and in-context learning, which is part of this broader trend towards scaling compute at inference time. We'll talk some about RAG. I've talked about RAG a lot in the past, but we'll get more into it here. LLM agents, multimodal LLMs, whose purposes go beyond just next token prediction, and evaluation benchmarks. So first up is scaling laws. So early on in the research, they just figured that bigger LLMs are better. Increasing the model size, the number of parameters, the data size, or number of training tokens, and the computational budget, or how long you train these models, just leads predictably to better performance. And that was true. And this is measured as lower cross-entropy loss on the holdout test set. But they found that there was a very specific sort of interplay between these 3 variables: the model size, or number of parameters, the data size, or number of training tokens, and the computational budget, or amount of training epochs. So there was a 2020 paper by Kaplan et al., and they found that test loss decreases as a power law function of model size, data size, and training compute, and that these trends were observed to hold more than 7 orders of magnitude. And the shape of the architecture didn't seem to matter as much as the scale of these 3 variables. So the ratio of network depth and width had a lot less impact on the performance of the model than just throwing more parameters, data, and training time. So this is why early on, the models just got bigger and bigger, and that was just the only truism you could really rely on. So GPT-2 was 1.5 billion parameters. GPT-3 was 175 billion. And GPT-4, I think it's an estimate, is 1.5 trillion parameters. The trick was to scale these three variables together. And they found that performance improves predictably when the number of parameters and the number of tokens, the training data size, were scaled together, but increasing the number of parameters significantly while keeping the dataset size fixed leads to diminishing returns due to overfitting. The study found that the performance penalty depends predictably on the ratio n to the 0.74 over d. N is the number of parameters and d is the tokens, implying that the dataset size needs to grow sublinearly with model size to maintain optimal performance. So when they found that ratio, they realized actually maybe there's a little bit of fiddling so that the three variables don't just scale linearly together, just larger models, larger data sets, and more training, and that there's this perfect ratio that they could dial in to optimize training the most performant models. And so DeepMind came up with this chinchilla scaling law. I don't know why chinchilla. And it focused on finding the optimal allocation of fixed training compute budget. So they found the perfect ratio of these three things. And it implied that GPT-3 and larger, earlier models were undertrained relative to their size. So they should have been trained longer and on more data. And they proved this with the chinchilla 70 billion parameter model compared to the GPT-3 175 billion parameter model. So less than half the size, and it outperformed it. And so they found that the most compute efficient way to train a model is training very large models on slightly less data compared to what may seem necessary, and stopping before the model fully converges on the training data. Now, all this stuff about training efficiency is important. It doesn't seem important. Like you can just train a model all the way till convergence on as much data as you can possibly muster for as large of a model as you can possibly muster and so forth until it converges with your tensor board graphs and whatnot. The reason this stuff matters is that with these large language models, training is very expensive, like billions of dollars, expensive in terms of money. And so is inference once you launch these models. But right now, everything we've talked about specifically is the optimal ratio of model size, data size, and epochs to train to milk out the best cost per training. They'll train these models for very long periods of time and on very large GPU clusters or TPU clusters, and it will cost them a lot of money. So this stuff counts. But at inference time, when you're running these models in the cloud, ChatGPT or Gemini on their website or on the mobile app, there's a cost to inference. And there is a different ratio in terms of the model size and maybe overtraining it on more data. And so if you want to optimize for inference costs, you might want a smaller model trained significantly longer or on more data to try to approximate the same performance. And so these companies will run some calculations as to how much they think their model is going to be used by consumers or companies relative to how much it might cost them to train the models, and they'll come up with the perfect ratio of training budget versus inference budget so that cumulative cost of inference over a model's lifetime could significantly outweigh the initial training costs. So the cheapest training regime is large model on slightly less data or slightly fewer epochs than what would seem normal, stopping before convergence. A chinchilla optimal model might be the opposite. So it would be a smaller model trained over more data for a longer period of time. And we first saw this really with the Llama series, Meta's Llama models, LLAMA. They were trained intentionally on far more tokens per parameter than Chinchilla recommended. So for Llama 2, it was 2 trillion tokens. Llama 3 was 15 trillion tokens. And this improved inference costs. So one analysis showed that training a 13 billion parameter model expecting 2 trillion inference tokens could save 17% of total flops, FLOPS, by using the smaller model. And we'll talk about later, this isn't the only way they're working with optimizations. They're also working with inference time compute or test time compute, which is dedicating more computational resources during the text generation process itself, allowing the model to perform multiple reasoning steps, sample different potential answers, critique its own output, and doing these inference time steps, it can achieve better results for complex tasks, which increases the latency or per query cost, but improves the quality of the output and potentially allows them to reduce some on the training side of things. Next is emergent abilities. By the way, if I seem out of breath in this episode, it's because I'm recording it at a treadmill desk. Aristotle, Nietzsche, Kant, and Thoreau all believed walking was essential to thinking. Nietzsche said only thoughts reached by walking have value. So I use a walking desk while I study, record, edit, or work. It improves focus, energy, alertness, and mood by increasing blood flow and endorphins. You should try one too. Meet your fitness goals while you study machine learning or work on your ML projects. See a link to my favorite walking desk setup at ocdevel.com/walk. That's ocdevel.com. Next is emergent abilities. And this is talked about a lot. You'll see this in textbooks or YouTube series about large language models. I think this is the magical aspect of LLMs. When you do the first pre-training step, we'll talk about training later, and you're just training it to predict next tokens. And then you do the fine-tuning step, where you're fine-tuning it to specific tasks like answering questions or writing code. What you have then is a model fine-tuned to a specific series of tasks. And it's actually incredible that it can infer or reason outside of the specific examples it's seen. So yes, it understands the English language. Yes, it understands you've given it 10 examples of answering questions in the English language. But then if you ask it a question for an answer it's never seen before, and it can infer, fill in the gaps, the real answer to that question, it's actually quite an amazing phenomenon. And it amazes even researchers, I think. And so they call it an emergent ability. But they have a handful of specific emergent abilities they use as example. Emergent abilities, they're not quite as present in smaller scale models, but they appear sharply or abruptly in the training of larger scale models. So as you're training the larger LLMs, the capacity to perform these emergent abilities during inference arises all at once at some point in the training cycle. And so they list a handful of these commonly known emergent abilities. One is in-context learning, or ICL. It's the ability to perform new tasks based only on examples provided in the prompt at inference time. So that might be one-shot or few-shot prompting. You give it an example scenario of A leads to B, and then you give it C, therefore, and it can infer D. In-context learning. Instruction following, the ability to execute natural language instructions for tasks it's not seen during training. Multi-step reasoning. So they've learned through time, through tinkering with various prompts and this whole world of prompt engineering, that multi-step reasoning significantly improves the performance on tasks requiring sequential reasoning, like arithmetic, common sense, symbolic manipulation. So as a prompt engineer, you nudge the model to take multiple steps in its output, or you have some structure in place that sort of does that on behalf of the model, and it will improve the performance, which is cool. It's almost like an actual human student showing their work improves the performance or the accuracy of the result. We tell students to show their work for a reason. Chain of thought prompting. We'll talk about chain of thought later, COT. It's very similar to multi-step reasoning. So these emergent abilities seem to arise after a certain threshold of model scale, number of parameters in training data, and training. And the assumption is that larger models just learn more complex patterns, world knowledge, reasoning structures, and thought pattern sophistication that these smaller models can't do. This concept of emergent abilities is actually contested in research. A 2023 Schaefer et al. Paper suggests that it might be a mirage created by the choice of evaluation metrics rather than some fundamental property of model scaling. I won't get into this too much because I think it's a little bit splitting hairs, but they talk about the metrics which are used to evaluate the performance of these models being nonlinear or discontinuous. The idea of these emergent properties appearing all at once late in the training phase and for large models is a consequence of the metrics being binary. You either passed the test or you didn't. And so it discounts the sort of stepwise learning it takes to learn these more complex patterns until, bam, it can answer the questions more confidently. Next up is changes to the actual transformers architecture. So transformers is a series of self-attention modules followed by feed-forward networks and some nuances along the way. Normalization and positional encoding, residual connections and stuff. But the mixture of expert is not a nuanced addition. It is a large addition. What it is, an expert is a sub-network designed to handling a specific topic, let's say. Maybe one expert is good at math, and another expert is good at philosophy, and another expert is good at answering questions. Now, these experts, the number of experts and what each expert represents is a black box. So you don't know what they're actually focusing on, and it's probably not topics. It's probably something more complex, latent space that a human wouldn't possibly understand. But they determine the number of experts in advance, and somewhere along the network path during training time or inference, the right expert is chosen for the given task at hand, and the other experts are deactivated, or they're called dormant. And so only one expert is activated at a given time. And this improves computational performance, efficiency. You only have to use one sublayer at any given time. So they call this conditional computation. It's a design philosophy. So instead of activating the entire network at every input, a mixture of experts model only activates specific experts deemed most relevant for that input. And this dramatically increases the total number of parameters in a model without a corresponding linear increase in computational cost, or flops, required to process each input token. So I'm looking at the DeepSeek R1 model, and the total number of parameters is 671 billion, but the activated number of parameters is only 37 billion. What that means is when you run the model at any given time, only 37 billion parameters are live. And so it's a lot faster. So these mixture of expert layers, they usually replace the standard feed-forward network layers within some or all of the transformer blocks. And it has two primary components. The expert, which are independent neural networks, and they're typically just feed-forward networks. And the number of experts per block varies from model to model. It's 8 in mixtral, but there can be hundreds or thousands of experts. And the total number of parameters across all the experts, of course, adds up to the number of parameters of the network. And then the second component is called the router or gating network. And it's a very small neural network that's usually a linear layer followed by a softmax function. And it just determines how the tokens are processed by the experts or which experts to activate. And so it takes an input token, like the output token from the previous attention layer, and it outputs a signal that controls expert activation. And one of the big efficiency gains that Mixture of Experts implements is through this thing called sparse activation. So the router network calculates a score or probability for each available expert, indicating that it's suitable for processing this particular token. And a selection mechanism is used to determine which experts to use. It's usually like the top one or two. So you might use two experts in any given token. And then the output of those two experts are combined through something like a weighted sum based on the router's score to produce the final output of the MOE layer. So this is called sparse activation. So with MOE transformers, you can have really large models, which, as we saw with the scaling laws, large models matter. And the largeness of these models is maintained because even though only one expert is active at a given time, through training and the activation of a particular expert, still the overall intelligence is roughly maintained throughout the network architecture at large. It's just that any one pass is more efficiently computed. So training can be faster and more computationally efficient. Inference can be faster, especially for lower batch sizes. And then experts can specialize in particular things. We don't really know what these are, but they may be something like different types of data, linguistic patterns, knowledge domains, or computational functions. And the analogy here is if you have a task and you go to a Mensa, ultra intelligent, high IQ person, versus taking that same task to a company, a team that has a manager who will hand it off to any number of the specialists under him who have studied one particular topic their whole lives. Okay, so the downsides of mixture of experts models. One is that even though during training and inference, only one expert route is active during a single token pass, the whole model still has to be in VRAM or RAM. It still has to be loaded in your GPU. So if you tried tinkering with local models, per the last few episodes when I talked about vibe coding, if you tried downloading Ollama and DeepSeek R1, for example, and maybe you looked at that active number of parameters and you were disappointed that it wouldn't load into VRAM or RAM. And that is because the whole model does have to be loaded into RAM. Efficiency is not at the RAM level per se, it's at the compute level. Another downside is training becomes a little bit more difficult for these things. There's this concept of load balancing, and that's making sure that all the experts receive the same amount of training data and computational load. So it's making sure that no one expert is relied upon too heavily. But this is, if you recall from a long ago episode on neural networks, maybe akin to L1, L2 normalization or dropout. It's like a tech, turtles all the way down with these things. So now we're dealing with modules and layers as opposed to individual layer regularization techniques. Now we have to build in these complex load balancing mechanisms that makes sure all the experts are participating equally in the training process. And some techniques they have are auxiliary loss functions to encourage more balanced routing and hyperparameter optimization on the number of experts. Another issue is communication overhead. So because these modules and these layers, maybe you want to train them separately and in parallel, they may reside on different GPUs or TPUs. So you have to have systems for routing the tokens to the correct experts. And this introduces communication overhead. So you have to build efficient systems designed for communication protocols and mitigating bottlenecks and such. And also MOE architectures make overfitting a little bit more likely, simply because you're adding more parameters to the network, increasing the size. And so you have to be more mindful of regularization. I believe most, if not all, modern LLMs use mixture of experts layers now instead of standard feed-forward layers. There will be some combination of both feed-forward and MOE layers. Okay, next up is training, tuning, and alignment. There's 3 steps in the training of these models. The first step is the pre-training phase, unsupervised pre-training. And this is what you think of when you think of training a model, transformer model. It's learning next token prediction. So you give it the internet, right? There are all sorts of data sets out there. There's Common Crawl and C4. You give it the internet and you train it for a very long time. This is the most expensive training step. This is generally what they do when they're training a model for months and months. And most of what it's doing is learning to predict the next token in a sequence. The cat sat on the blank mat and adjusts its score accordingly. It's unsupervised because the correct answer is the next token, but there's not some labeled data set of labels or ground truth values that correspond to sentences or tokens. It's just predict the next token. And there's some sophistication involved in this. I covered that in the Transformers episode and the RNNs episode. But that's the first step. Now you have a pre-trained model. And they call this a foundation model. A foundation model. It's just models pre-trained on mountains of raw data. And by the way, don't confuse that with frontier model. Frontier model means like the newest and greatest of foundation models. So current frontier model would be Gemini 2.5 Pro and GPT 4.5 and so forth. Once you're done with that, you can't use it for anything except for auto-completion, like you're finishing a text message or an email, sure. But that's not the real value of LLMs. The value is executing a task, performing a specific task, answering a question, writing code, and so forth. And so you fine-tune these models after that using something called supervised fine-tuning, SFT, supervised fine-tuning. And that is the process of adapting a pre-trained LLM by continuing its training on smaller curated data set of labeled examples specifically designed for a target task or behavior. So it's a supervised learning process. Somebody has to generate a data set of very high quality prompt response pairs. So questions and answers, for example. Who is the 40th president? And it has to say Ronald Reagan. A whole giant data set of task-specific prompt response pairs. So there's question and answering, there's summarization. The data set would be articles or chapters, and then a human written summary. And then during training, the model processes the input tokens, generates the response, and calculates the difference or loss between its output and the correct label. And then the error signal is used through gradient descent to update the model's weights, just typical neural network stuff. Question answering, summarization, code generation, medical Q&A. And while it's training on these specific data sets, it's also learning the domain and the jargon and the nuances and the deeper knowledge of this particular vertical. So if it's trained on a code generation data set, maybe you have the inputs being a comment saying implement the following function, and it outputs a JavaScript function. It will learn JavaScript in the process, anything it didn't already know during the unsupervised pre-training step. And if you were here during the early Hugging Face days, you'll recall that we had to download a task-specific model for any one of these tasks, summarization, question answering. And modern frontier models will basically have all of these data sets all in one. It will train across the entire, after GPT or Claude or Gemini are done with the pre-training phase, it will then fine-tune on every task-specific supervised fine-tuning data set out there so that it could become a general purpose model. But if you need a model specifically geared towards one task, like code generation might be one of the most popular task-specific model tasks out there, you might want to limit it to just handling that particular data set. Coming up with these data sets is obviously no easy task. These days, there are lots of data sets to work with that have been curated and developed over the years and decade. It is very easy to overfit models on the fine-tuning data set, especially for small models, and so it can lead to poor generalization on unseen data. And then there's this thing called catastrophic forgetting, where a model loses some of the general knowledge that it has acquired during the pre-training step as it specializes on the new task. So it becomes a little too focused on the new task at hand, and it forgets broad world domain knowledge. And so managing this stuff all comes down to hyperparameter optimization. So I have a whole episode on hyperopt, and that includes things like the learning rate and the number of epochs. Overfitting and catastrophic forgetting aren't new issues, but they do pop up as you fine-tune, as your data set sizes increase, as your model sizes increase, as you saw with the mixture of experts. Okay, reinforcement learning from human feedback. RLHF. Build the future of multi-agent software with Agency, A-G-N-T-C-Y. Agency is an open source collective building the Internet of Agents. The Internet of Agents serves as an open source, interoperable collaboration layer allowing AI agents to discover, connect, and work seamlessly across diverse frameworks. For developers, this provides standardized agent discovery tools, seamless protocols for inter-agent communication, and modular components to effectively compose and scale multi-agent workflows. Join pioneers like Crew AI, LangChain, Llama Index, BrowserBase, Cisco, and dozens more in this effort. Agency is actively dropping code, specs, and services right now, all open source, no strings attached. Build with other engineers dedicated to high-quality multi-agent software. Visit agency.org and add your support. That's AGNTCY.org. Okay, reinforcement learning from human feedback, RLHF. And this is typically the third training step, the third phase of the training cycle. First one's pre-training, second is fine-tuning, and then we do reinforcement learning from human feedback. Okay, so the goal of RLHF, the goal is alignment. And you'll see things like the alignment problem in LLMs. People talk about the alignment problem of AI. I always thought that alignment had specifically to do with, racism and sexism, like curbing bias in LLMs or preventing evil killer robots. What it is more general. It's actually just making sure that models align with human preferences. It's training the model on certain qualities like helpfulness, honesty, harmlessness, and these are nuanced attributes that are hard to capture with static labeled data. It's really hard to capture whether something was helpful in a pre-built data set about code generation or question answering, or whether it was accurate. You may have a whole data set on questions and answers, but maybe some of those answers are wrong, or maybe they weren't thorough enough. Maybe they just didn't align with human preference. Maybe they should have been tighter answers, simpler, just the facts, please. RLHF's entire goal is alignment, and alignment is ensuring that a model's outputs are consistent with human values and intentions. Trying to make the model a better conversational partner, a more reliable source of information, and also, yes, less likely to generate harmful, biased, untruthful content. And so RLHF involves 3 stages. The first is to start with the pre-trained and supervised fine-tuned model. Next, we collect human preference data. So this pre-trained fine-tuned model that we've already built up is now going to generate different responses for the same input prompt. Maybe you'll use a different temperature or annealing or sampling, some technique to generate 2 different responses. And a human labeler will rank the responses based on various criteria. Was it helpful? Was it unharmful? Was it truthful, understandable, and so forth? And relative to each other. So it's a scoring system. So it's comparative feedback. Then we train a reward model, a real reinforcement learning model. So go back to the RL episode. And a common one is PPO, proximal policy optimization. I believe I mentioned that model in that episode. It was the sort of new cool RL model that was happening when I last was looking at RL in like 2018 or 2020. So this PPO model, our reinforcement learning models, trained on the human preference data. And it's trying to predict a scalar reward score for any given prompt response pair. So it's learning to mimic the human preference judgments captured in the rankings. It's learning to act like the human. It's learning to play the preferences that the human played out as if it was a video game. And this guy is now a video game playing AI agent. And of course, a high score indicates the response is more likely to be preferred by the human. Then you do another fine-tuning phase of the original LLM, the pre-trained and SFT fine-tuned model, where this RL model, the PPO model, is actively watching the outputs that the model generates, and it's scoring them based on these predicted scores. And it's like a little teacher telling the model good, bad, good, bad. And if I'm not mistaken, I could be wrong about this, I think that the RL model actually can reach into the architecture of the LLM and manually adjust the weights based on the predicted score. So I think it's doing a little bit of surgery on the model. It's kind of like this little droid that's zapping the neurons inside of the model as it generates outputs. I could be wrong about that, and instead it's simply providing some sort of a feedback that the model can use standard supervised learning to backpropagate error during the training process. And I believe these RL models can adjust the weights of the LLMs while they're live. And I just did a search on that, and that is true. That's correct. So I'm not sure to what extent this is actually used in the wild, but my gut tells me, I remember OpenAI saying that you're going to be impressed with how much ChatGPT improves over the next weeks or months after they launched a live one. I think it was 4.0. And my assumption here was that it was generating updates to the model live with every time somebody did a thumbs up or a thumbs down, when it generates two responses, split screen in chatgpt.com, and says, which one do you like? And also these data sets, I don't know if you've ever seen the company dataannotation.tech. I see a lot of ads for them. My ex actually did work with them, and that's what they do. They generate scores for these various values like helpfulness and bias and stuff for textual content. And then I think that they're like contracted out by some of these major LLM players to provide that back for RLHF training data. So the big benefit of RLHF is that it captures something that text data sets don't capture. And that is value, nuanced, subtle preferences for responses that would be really hard to capture in text. And as a consequence, the introduction of RLHF has bolstered the performance or the value of outputs significantly, and in a way that before the introduction of RLHF was impossible to capture. And evidently, RLHF can make really big changes very fast that are very valuable changes to the model. They call this parameter efficient. So it doesn't matter if your neural network is large or small. These data sets and trained PPO RL models can really improve the performance of those LLMs. Okay, so what are the downsides of RLHF? It's complex, it's resource intensive, you have to collect high quality data. It has to be consistent data. It's sometimes hard when somebody's staring at the screen all day and doing hundreds of these tasks to think really critically about how helpful or unbiased some response was at the 11th hour. It introduces a lot more sophistication to the training process of a model. This makes it difficult to implement and tune correctly. And there's a big concern of reward hacking, or you've ever heard the term specification gaming. Specification gaming. Way back in some of the philosophical episodes, I talked about the paperclip maximization theory. It's this sort of cheeky idea where if you tell a robot, if it's a misaligned AI, and its entire premise is to maximize the output and sales of paperclip for Paperclip Co., then what's to prevent the AI from learning how to suck in the entire universe and absorb all the raw materials and create the big crunch and destroy the universe and so forth? That was thought of as a silly philosophical idea for a while there. But as RL has been used more extensively in research and academia and in industry, they've actually found this to be a real concern. RL tends to find shortcuts to maximize the goal that was given it. And so you have to make sure that goal is really clever and specific and nuanced and captures a lot of blah, blah, blah to prevent it from reward hacking. And this problem is called specification gaming. And so the LLM will find ways to exploit the reward model to get high scores. One thing they found is during the early days of this, while they were exploring it, it was generating really verbose, unhelpful answers because the human reward labelers thought that verbosity probably indicated truthfulness and helpfulness. I'm not going to read this whole thing, but it looks like it knows what it's talking about. And so LLMs learned to skip the truth by doing a filibuster, and humans were accidentally labeling that as good. So there's whole techniques and hyperparameter optimization and overseeing the data sets and so forth to make sure that this reward hacking doesn't happen. Now let's talk about reasoning and in-context learning. So there are specific tasks where an LLM benefits greatly by enabling complex multi-step reasoning. These are particularly for logical deduction, mathematical calculation, common sense understanding applied over multiple steps, code, and because so many of these components listed really present themselves in any type of task where you're asking a question, the typical use case of ChatGPT and Gemini, more and more they are adding this reasoning phase to LLMs. And it's not architectural. There's no modification to the neural network. It is simply a modification of the way that the model is prompted. Now, this began in the early days with prompt engineering. For a while there, prompt engineering was a really valued skill. In fact, there were jobs out there for prompt engineering. And I still think everybody should learn prompt engineering. I may or may not add a segment for some top tips in prompt engineering in this episode. We'll see if we have time. But it's the difference between a good response and a bad response. Partially because these models were trained on certain data, and that data maybe was a little bit more specific than the average human query, and partially because a sequence of thinking steps prior to giving an answer in humans helps with formulating a correct response. And either the training data bears that out, that showing a sequence of steps leading to a response is what the model is trained to work with for generating the right response, and or, per the emergent abilities mentioned previously, telling the model to show its work step by step as it's generating a response similar to a human without anthropomorphizing these models too much, but they are trained based on our language. Surely that training incorporates some metaphysical aspect of language use. Showing steps, step by step, as it's generating responses leads to better responses. It can correct itself. It can cross-check itself. It can look at tokens and steps previously. That glimpse back acts as a language level self-attention mechanism, almost like extrapolating the attention mechanism within the neural network outward to the language level. Having that token visible in its context in the generation of the next token acts as a sort of token level attention mechanism. And so early prompt engineers really knew the tricks of the trade. And one of the big tricks they applied was they would simply append the phrase, "let's think step by step," or "think through this step by step." So they would type out their prompt, and at the very end, they'd just enter and then say, "let's think step by step, Control Enter." And the results would be significantly better. And by the way, prompt engineering, there was this guy on Reddit recently that did geoguessing. He put a flag in some rocks, and it was in Nepal, and said, try to guess the location of this flag to GPT-03, and it guessed it within a mile radius with no indicators whatsoever. And everybody on Reddit tried to do it with their own pictures of ball and their lawn and stuff, and nobody could replicate it. And then somebody said, guys, look at the prompt. And they went to the original prompt and they copied and pasted it, and it was like 10 paragraphs long, and it was worded in such a strange way that nobody would have thought to word it. And they pasted it, and then sure enough, they all got great performance for the model geoguessing their own photos. And that just goes to show that prompt engineering is alive and well, and it's critical especially if you're using this for coding, vibe coding like the prior episodes. There is a button. If you use Rue code, which you hear me peddle all the time, there's a button before you click submit, star symbol, the classic AI icon, that will rewrite your prompt using well-known prompt engineering techniques, and that will improve the quality of the code output more than if you had just clicked submit. So prompt engineering, very important. Learn it if you can. Look up one of the guides. Each model has their own, but generally 80% of the prompt engineering guidelines out there apply across all the different models, and it makes a very big difference. And so chain of thought prompting was that these frontier model designers, ChatGPT, Gemini, realized how valuable very specific prompt engineering techniques were and made sure that those were integrated with your prompt. So you would say, who was the 40th president, and it would append think step by step under the hood so you don't see it. And that's not all what chain of thought prompting is. So let's get into chain of thought. But that was the precursor to this revolution. Chain of thought is a technique that guides the LLM to explicitly articulate its reasoning process by generating intermediate steps before providing the final answer. It encourages the model to think out loud, mimicking how a human might solve a complex problem. There are other techniques of chain of thought. You can provide a few examples demonstrating the desired task. So this is called few-shot prompting or few-shot chain of thought prompting, where each example explicitly shows the step-by-step reasoning process leading to the answer. Or you can do zero-shot chain of thought, which was the one I said, let's think step-by-step, adding that to the end of the query, and it will trigger the model to generate a reasoning chain. And some more complex chain of thought, I don't know exactly how they work, but you'll see with O4 Mini High, it will iterate over these chain of thought prompts. So it will go multiple steps, one after another, until it's confident it can give you a final output. I believe that the way that works is if at the end of a chain of thought, it implies that it needs to dig in deeper, then it will trigger the system to run it again until somehow it determines that it has the right answer. This chain of thought system dramatically improves LLM performance on a wide range of tasks: arithmetic, common sense, symbolic reasoning, obviously code. In vibe coding, you'll see chain of thought used for architect mode, for orchestrator. I think they use it for orchestrator mode. Anything where it needs to come up with a game plan, a step-by-step strategy. So by externalizing the reasoning process, it leads to more accurate results compared to directly asking for the final answer. And this is also valuable for generating a degree of transparency to the model's process that can help in debugging, interpretability, monitoring for safety and alignment purposes. Okay, there's a few variations of chain of thought, and for more advanced techniques that have been developed. One is called self-consistency. This involves generating multiple independent reasoning chains or chains of thought for the same problem using different temperature sampling, for example, and then selecting the final answer based on a majority vote among the conclusions reached by the different chains. This improves accuracy by mitigating the impact of the occasional faulty reasoning path. So it's like an ensemble machine learning model just for the chains of thought. And then there's tree of thought, or TOT. I've never personally seen this, or I don't think I've seen it. Maybe it's happening under the hood for some of these frontier models. But it allows the model to explore multiple reasoning pathways simultaneously. So it creates a tree structure. And at each step, the model can generate several possible next thoughts or intermediate steps, evaluate them, and decide which paths to pursue further using search algorithms like breadth first or beam search. So it's a far cry from standard prompt engineering. It is quite architectural. It's an architectural shift. But it allows exploration and backtracking, and it can handle more complex problems where a single linear chain of thought might fail. Obviously, a chain of thought is more computationally expensive than just standard inference. And so I think these frontier models are coming up with ways to be very intelligent about how much thinking time, how many steps in a chain of thought, whether to use chain of thought at all, automated on your behalf with these models in advance before triggering these things. So it's not a simple question that warrants a simple answer doesn't kick off one of these chains. Okay, I'm only halfway through LLMs, so I'm actually going to split this into another episode. So we're still inside of inference time training, test time compute, reasoning, that umbrella of territory. Leaving off with chain of thought, and then we'll pick up with in-context learning, like few-shot prompting or one-shot prompting in the next episode on LLMs Part 2. I'll see you there. You've been listening to Machine Learning Guide, and I'm your host, Tyler Ranelli. MLG teaches the fundamentals of machine learning and artificial intelligence. It covers intuition, models, math, languages, frameworks, and more. It's a start-to-finish audio overview of machine learning principles. Then for topics needing more depth or which are best learned visually, I provide a syllabus of resources at ocdevel.com/MLG. That's ocdevel.com. You'll notice that episode titles start with either MLG or MLA. G for guide teaches theory and fundamentals, where A for applied teaches industry and practical tools. You can listen to either or both depending on your goals. If you want to support the show, like and subscribe in your podcatcher, whether iTunes, Spotify, or YouTube.